Have you ever pondered why time runs differently on a mountain peak compared to the sea level? It's a question that might seem outlandish at first glance. After all, isn't time supposed to be constant, ticking away at the same pace wherever we are? But, as it turns out, the reality is far more complex and fascinating. In our everyday lives, we take the concept of time for granted. It's always there, unchanging, reliable. Yet delve a bit deeper into the realms of physics, and you'll find that time is not as straightforward as it seems. Enter the world of gravitational time dilation, a mind-bending concept that challenges our everyday understanding of time. It's a concept that hinges on a surprising relationship, that between time and gravity. So buckle up as we take a journey through the intriguing world of time dilation. Strangely enough, gravity, the very force that keeps us grounded, also influences the flow of time. The phenomenon we're about to unravel here is gravitational time dilation, a concept rooted in Einstein's theory of relativity. To truly appreciate this mind-bending concept, let's start from the beginning, with the theory of relativity itself. In a nutshell, Einstein's theory of relativity proposes that the laws of physics are the same for all observers, regardless of their motion or position. It's a bit like saying that whether you're on a speeding train or standing still, a game of catch will play out in the same way. This theory also brought forth the concept of the space-time fabric, which is essentially a four-dimensional canvas that represents our three dimensions of space and one of time. Picture a stretchy sheet that can be warped and twisted. Now imagine a heavy ball placed on this stretchy sheet. The weight of the ball creates a dip or a curve in the sheet. This is how gravity works according to the theory of relativity. It's the bending of space-time caused by massive objects. But what does all this have to do with time? Well, when gravity bends space-time, it also affects the passage of time. The stronger the gravitational pull, the slower time passes. Think of it like walking uphill versus walking on flat ground. The steeper the hill, or the stronger the gravity, the slower you'll move, or the slower time will pass. This means that time actually moves slower the closer you are to a massive object. So, if you were to place a clock at the top of a mountain and another at sea level, the clock at sea level would tick slower than the one on the mountain. This isn't a perceptual trick or an illusion. It's a real, measurable effect known as gravitational time dilation. It's been tested and confirmed by experiments, and it's a fundamental part of how our universe works. So, because of the way gravity interacts with the fabric of space-time, time ticks slower closer to a massive object. This is the essence of gravitational time dilation. Let's now encapsulate what we've learned about gravitational time dilation. This mind-bending concept, born from the genius of Einstein's theory of relativity, tells us that gravity influences the flow of time itself. The stronger the gravitational field, the slower time ticks away. Imagine the fabric of space-time as a trampoline. A heavy object like a bowling ball will cause the fabric to bend or warp. Now consider a tiny marble rolling along this warped surface. It doesn't move in a straight line, but in a curved path influenced by the bowling ball's mass. This is how gravity works. It's the bending of space-time by mass and energy. This bending also affects time, slowing it down near massive objects. So the next time you find yourself atop a mountain or a skyscraper, remember, you're living, albeit minutely, in the future compared to those at sea level. Such is the fascinating world of gravitational time dilation.